Hey everyone, welcome back to Real Analysis 1. This will be lecture 8 of the course. And in this section, we're going to discuss the limit superior, the limit inferior, and Cauchy sequences. So this will be a slightly longer lecture. There'll definitely be a part A and part B. And so we'll begin with the limit superior and inferior. So let's go ahead and jump into it. We'll call this section 2.5, limit superior and inferior, and Cauchy sequences. So let's go ahead and begin by discussing the limit inferior and superior. And let's go ahead and try to develop this idea. So let's let Sn be a sequence in R. Okay, so sequence of real numbers. And for each natural number k, so for each k in n, the natural numbers, let's define a sub k equal to the infimum of s sub n such that n is greater than or equal to k, and b sub k equal to the supremum of s sub n such that n is greater than or equal to k. Okay, so remember this infimum and supremum, that's going to be the least upper bound and the greatest lower bound. Okay, and so recall that for a non-empty subset, so for E in R with E not empty, okay, so for a non-empty subset of E, the supremum of E, right, the supremum of E is the least upper bound of E. It's the least upper bound of E. It's the least upper bound of E if it's bounded above, if E is bounded above if E is bounded above, and it's infinite if it's not bounded. Right? So this is just a reminder of what that means. Okay. So from the definition, a sub k will be less than or equal to b sub k for all k, right? So what this is saying is that the infimum of the set is going to be less than or equal to the supremum of the set for the whole set. Now that should be relatively obvious based on what the infimum and the supremum are. Okay, so a sub k is less than or equal to b sub k for all k. And also, right, and also, if you think of the sequences a sub k and b sub k, if you think of those as sequences, they're going to satisfy, a sub k is less than or equal to a sub k plus 1, right? So as I remove elements from the sequence s sub n, I mean, in this case, I'm always removing the smallest element, right? So that means the element, you know, this is basically a monotone increasing sequence, this a sub k here. And b sub k will be the reverse, right? b sub k will be greater than or equal to b sub k plus 1. And this is going to be true for all k. Okay, just by the way that these two sequences are defined. Okay, now let's explore this a little bit just to make sure we can see this, because a lot of the theorems and things we're going to develop specific to limit inferior and superior are going to kind of they rely on the fact that this is true. So let's explore this. So to see this, in case you can't see it, let's let E sub k equal the set S sub n such that n is greater than or equal to k. So all we're doing is we're saying, okay, for some k, let's truncate the front of the sequence up to k, right? So we'll include all the terms after the kth term. Okay. So then, obviously, E sub k plus 1 is a subset of E, right? And if b sub k is equal to the supremum of E sub k, the set E sub k, if B sub k is equal to the supremum of this kth set E, then S sub n, right, will be less than or equal to B sub k for all n greater than or equal to k. Okay. Right? So in particular, right, let's dive down one more level. All right, we'll say in particular, S sub n will be less than or equal to B sub k for all n greater than or equal to k plus 1. Right? And so therefore, B sub k plus 1 is going to be equal to the supremum of E sub k plus 1. Right? That's the definition, which would be naturally less than or equal to B sub k. Right? And then the same argument can be developed for the increasing sequence A sub k. Okay? So this same argument can be developed for A sub k, which is an increasing sequence. Okay. All right, so that kind of takes care of that. Right, so A sub k is monotone increasing and B sub k is monotone decreasing, as we said. Monotone increasing, and then B sub k is monotone decreasing. Okay, so remember, A sub k is the greatest lower bound on the set n as we move up, through the sequence. Right, as we successively remove elements from the front of the set. Okay, and B sub k is the least upper bound of the set under the same mechanism. Okay, so given that, I think we can define what we mean by the limit superior and the limit inferior. So let's take a look at that. So this will be a definition. Okay, we're going to let S of n, we'll let S of n be a sequence in R. Okay, then the limit superior, so the limit superior of S of n, and we can denote this, denoted by, it's usually just denoted as a limit as n goes to infinity with a bar on top to in for the superior, the upper. Right, so the limit superior, denoted like this, of S of n, is defined as, so we say the limit as n goes to infinity, the limit superior as n goes to infinity of S of n is equal to the limit as k goes to infinity of B sub k, which, if you recall, is the B sub k, remember, is the supremum. So recall, well, I'll bring it up here. B sub k was equal to the supremum of S sub n such that n is greater than or equal to k, right? Right, and so what we're saying here is that the limit superior of S of n is equal to the limit as k goes to infinity of B sub k, which is equal to the infimum for all k natural numbers of the supremum of this set. Okay, so B sub k is monotone decreasing, so it's the infimum of the supremum of these elements. Okay, so B sub k is a monotone decreasing set, so if I if I take the limit of that, then it's equivalent to identifying the infimum of this set here. Okay. And the limit inferior of S of n is kind of the reverse, right? And I'll write the denotation here. We write that as the limit as n goes to infinity, and we usually put the bar under the word limit. Right, so the limit inferior is equal to the limit as k goes to infinity of a sub k. So that means we're talking about the supremum of all k in n of the infimum of S of n such that n is greater than or equal to k. So this can be a tricky concept. Right, but the key idea here is that b sub k is monotone decreasing. So the limit as k goes to infinity is going to be the infimum of all this. And a sub k is monotone increasing. So the limit of that sequence, I mean, as you go further and further out in the a sub k sequence, you're actually going to be that limit is going to be the supremum of all of this. Okay. So kind of, it's almost like the reverse, right? So you've got the infimum of the supremums, and you've got the supremum of the infimums. Right, so it's a little bit of a tricky concept. Let's do some examples and see how this works in practice. Let's take a couple of examples. Sometimes the examples we look at can be, well, hopefully they're always instructive, but sometimes it's really in the examples where the concept can click. Okay, so let's take a look at an example here. Let's consider this sequence 1 plus negative 1 to the nth power for n equals 1 to infinity. So this sequence. Okay. And so we can let s sub n equal 1 plus negative 1 to the nth power. Okay. And so we know that s of n is equal to 2 if n is even. And s of n is equal to 0 if n is odd, right? Right. So if n is even, then this becomes a positive, and you got 1 plus 1. If n is odd, this is negative 1, and you've got 1 plus negative 1, so 0, right? So this is really like the only two values of the sequence. Okay. So then what about a sub k? Well, a sub k is equal to 0, right? Remember, well, hold on. So a sub k, remember, is the infimum of s sub n such that n is greater than or equal to k. Now, that's equal to 0, right? It's the smallest value in the sequence beyond the kth term. That's what a sub k is. And so that's obviously equal to 0. And b sub k, what's b sub k equal to? Well, that's the supremum of s sub n such that n is greater than or equal to k. And that is going to have the same value throughout as well. That's going to be equal to 2. Okay. Right, and so this is kind of a simple example, but it helps to clarify the concept. And so the limit superior of s of n is equal to the limit as k goes to infinity of a sub k, which is the supremum of the, for all k and n, of the infimum of s of n such that n is greater than or equal to k. Right, and we know that that's equal to 0. Oh, sorry, 2, backwards. My bad. Okay. And, right, so this is the limit of this sequence here, right? So, and then the reverse one, the limit inferior is equal to the limit as k goes to infinity of b sub k, which would be equal to the infimum of all k's of the supremums of s of n such that n is greater than or equal to k. And that, of course, is equal to the 0. There's only two values in the sequence, so one is one and the other is the other. Okay. All right, cool. Very good. Let's take a look at another example. Sort of similar, but maybe a little bit trickier. Let's take a look at another one. Okay, let's consider this sequence. N times 1 plus negative 1 to the nth power. Okay, so this sequence here. And so what is S of n here? So S of n would be equal to n times 1 plus negative 1 to the nth power, which, again, this is an oscillator. So it's 0 if n is odd. Right? Because if n is odd, then you've got, well, whatever n happens to be, and then, but this would be 1 minus 1. So whatever n happens to be times 0 is 0. Now, what happens if n is even? Well, if n is even, then this piece in here becomes 2. And so it's 2 times whatever n happens to be. So really, S of n is going to go on two branches. On the one hand, all the odd terms are going to be 0. On the other hand, all of the even terms are going to be 2 times the value of n. Okay. Right, and so we can let E sub k equal, right, S of n such that n is greater than or equal to k. Right, and then what do we get? Well, if k is odd, what do we get? We get E sub k. That set will be equal to 0, right? And then it'll be 2 times k plus 1, and then it'll be 0, right? This is the kth term, that's the k plus 1 term, and then this is the k plus 2 term, and then again it'll be 2 times k plus 3, and then 0, and so on, right? That's what that set is going to be if k is odd. Okay, if this guy here is odd. What if k is even? Well, if k is even, then you get 2k, comma, so the kth term would be even, so this would be 2 times k. And then the k plus 1 term must be odd, and so you would get 0. And then you would get 2 times k plus 2, and then 0 again. And then 2 times k plus 4, and then 0, right, and so on. And this is if k is even. Okay, if k is even. Right, and so A sub k, all right, let's think about what the A sub k, B sub k terms are. A sub k is equal to the infimum of E sub k. Right, so in either case, the infimum here is going to be 0, right? Right, the smallest, the least upper bound, the greatest lower bound is going to be 0. What about the B sub k's then? What about the B sub k? Well, the B sub k is going to be equal to the supremum of E sub k. And what is that? Well, this is clearly an unbounded set, right? In both cases, right? In this case, k is going to grow without bound. K is the natural numbers, indexed on the natural numbers. Anytime you're just multiplying it by 2, so it's going to grow without bound. So B sub k is infinity. Okay, and so then the limit inferior of S of n must be the supremum of these infimums, and that's 0. And the limit superior of S of n is going to be the infimum of all of these supremums, and that is going to be equal to, of course, infinity. Okay. Right, and so this sequence here breaks down and has a limit inferior of 0 and a limit superior of infinity, of an infinite limit superior. Okay, so that one's a little bit trickier, let's do another example. We're trying to develop some intuition about this. This is a little bit of a tricky concept. Let's take a look at this sequence. So negative 1 to the nth power plus 1 over n. Okay. Okay, and so in this case, s of n is equal to negative 1 to the nth power plus 1 over n. Okay, and so let's think about how that breaks down for odds and evens. So s of n will be equal to, in the case of n being odd, this will be negative 1 plus 1 over n. Right? If n is odd, then this is negative 1. And if n is even, it'll be 1 plus 1 over n. So this is n odd, and this is n even. Okay. And so let's think about laying out the first few terms of the sequence so we can kind of see what's happening. Okay, so I'm going to draw this on a line here. So the first term, when n is equal to 0, then you get, when n is equal to 1, you get, let's see, this would be negative 1 plus 1, so you get 0. So that's S1. Okay, now what is S2? Well, S2 is going to be, so n is even, in that case, so it would be 1 plus a half. So it would be 3 halves. Right, so I'm going to put those over here. All right, so we'll make this 1. Okay, so we know we're going to be kind of moving around 1 and negative 1. So we'll make that 1. And then down here, we'll make this negative 1. Okay, so the second term is going to be 3 halves, and so it's going to be somewhere out here, right? So S2, and we'll write 3 halves. Now this may not be to scale, but that's okay. And then S3 is an odd term, so it's going to be negative 1 plus a third, which is negative 2/3, right? And so it's going to be down here, roughly right around here. This would be S3, and that's going to be negative 2/3. And then S4, again, we're positive in this case, so it'll be 1 plus a fourth, so that's 5/4. So it's up here. Okay, and then we know that S5 will be a negative, and so that'd be negative 1 plus a fifth. And so it's going to be negative 4/5. So it's going to be right around here or something. Right? And so what's going to happen here if we continue on, right? So all of the even terms are going to get successively closer and closer to 1, right? So eventually I'm going to be adding 1 plus an infinitesimally small amount to it, right? So I'm going to be converging to 1 from up above here. And down below, I'm going to be I'm going to be basically going negative 1 plus some infinitesimally small amount. So I'm going to be doing the same kind of thing. I'm going to be kind of converging to negative 1 on the low side. Right? So what's this look like? All right. So that's kind of the visualization, right? You can kind of see on the even side. So certainly as a sequence, S of n doesn't converge in and of itself, but the odd terms and the even terms do appear as though they would converge. So I'm going to guess one of them converges to 1, the other one converges to negative 1, right? Right. So let's see what happens here. So we want to compute the limit superior and the limit inferior. And so we want to compute these. Let's let E sub k, right? So let's think back to first principles here. E sub k we're going to say is equal to 1 plus 1 over k and negative 1 plus 1 over k plus 1, and then 1 plus 1 over k plus 2, and so on. Right? Okay. And so this would be in the case where k is even, right? Right? So for an even k, therefore, I should write that. For k even, right? Right? So then B sub k would be equal to the supremum of E sub k, which would be equal to, if you just look at this, it's going to be 1 plus 1 over k, right? So that's larger than the second term. The third term compares with this one, but it's going to be technically smaller, right? So in this case, this is your V sub k. Okay, so it's equal to 1 plus 1 over k, right? And then what is A sub k? Well, A sub k is the reverse, so it's the infimum of E sub k. And what is the infimum of E sub k? Right, so if you think about this set, this is an infinite set, right? Right, the smallest term in here is going to be the furthest one out, and it's going to be one of the odd terms, right? So this is -1 plus some value, -1 plus some slightly smaller value, -1 plus some slightly smaller value, and so on. But at the limit, the absolute smallest thing in here must be -1. Okay, hopefully that makes sense. Okay, now what happens with odd k? Well, for odd k, then you get -1 plus 1 over k, comma, 1 plus 1 over k plus 1, -1 plus 1 over k plus 2, and so on, right? So it's kind of the terms are just kind of flipped a little bit, right? And here the B sub k, again, is the supremum of E sub k. And what is that? Well, in this case, it's going to be not the first term, it's going to be this one. 1 plus 1 over k plus 1. And the A sub k term here is going to be equal to the infimum of E sub k, and it again is -1. Okay. Okay, so for all k, so what can we conclude? Let's kind of, so usually you want to break it apart into the two sequences. Think about what B sub k means in terms of k even. Think about what k means in terms of k odd. And then kind of take those pieces and pull them back together and sort of summarize them. Right? So then what we can say is that for all k and n, A sub k is always -1. But B sub k may vary. So B sub k we'll say is equal to 1 plus 1 over k, or, and that's in the case of k even, or 1 plus 1 over k plus 1 in the case of k odd. Okay, so you've got this guy here, and then you've got this piece here. Okay, so let's then we can use this to calculate, or to just basically take the limit of those sequences to find the limit superior and limit inferior. So what we could say then is what? Then the limit superior, as n goes to infinity of s of n, is equal to the limit as k goes to infinity of your B sub k sequence, which we just saw, right, is either 1 plus 1 over k or 1 plus 1 over k plus 1. Now, sorry, let me do this properly. It's the limit as k goes to infinity of 1 plus 1 over k, or 1 over 1 plus, or sorry, 1 plus 1 over k plus 1. So it's this, or in parentheses, I'm going to write this. Now, does it matter which one you use here? Is the limit the same? Definitely, right? It doesn't matter. So if as k goes to infinity, this term becomes increasingly small, and this is equal to 1. So the limit superior is equal to 1, and the limit inferior, of course, is equal to -1. Both in both cases, A sub k is equal to -1, right? Okay. Very good. So those are 3 really good examples of this concept, right? And let's take a look at, there's a couple of theorems that we'll want to explore here. The first one, the first theorem is, you can kind of think of it as almost providing like a, not an alternative, but really kind of providing a deeper characterization of the limit superior concept. Right, so let's take a look at this theorem. Let's take a look. It's a little bit deeper expression of this thing. So let's let S of n be a sequence of real numbers. Okay, and there's going to be a couple parts to this. So the first part says, let's suppose that the limit superior of S of n is a real number, and then beta is equal to the limit superior if and only if, right? So we're saying, let's assume that the limit superior is a real number, i.e. that the limit superior is not infinite, right? Then beta is equal to that value, is equal to that limit superior if and only if, for all epsilon greater than 0, two things. There exists a natural number n naught such that S of n is less than beta plus epsilon for all n greater than or equal to n naught. Right, so that's the first part. And the second part says, given any natural number, right? So you give me any natural number, there's going to exist a k natural number with k greater than or equal to n such that S sub k is greater than beta minus epsilon. Okay. Okay, so let's make sure we follow this. So this is kind of like the epsilon delta sort of description of this idea. Right, so let S of n be a sequence in R. So we got a sequence of real numbers. And let's assume that the limit superior is a real value. It's not infinite. Then beta is equal to that value, is equal to that limit superior, if and only if for all epsilon greater than 0, I can find a natural number n naught such that S of n is less than beta plus epsilon for all n greater than n naught. So this is very much like a typical sort of limit theorem. Okay, and this should say and, given any n natural number, I can find a k natural number where k is larger than n, such that S sub k is greater than beta minus epsilon. So you give me some distance, then I can find a k that guarantees that S sub k is outside of that range, or above this value, above this beta limit superior. Okay, so that's the first part of the theorem. Okay, that's the first part of the theorem. The second part of the theorem, so is kind of a big theorem. Again, that's kind of why we call it an alternative characterization. Second part of the theorem says that the limit superior of S of n is equal to infinity if and only if, given m natural number and n natural number, there exists a k natural number, right? There exists a k natural number with k greater than or equal to n such that S sub k is greater than or equal to m. So this is a really easy idea, right? So basically the limit superior is equal to infinity if and only if the sequence is unbounded. Okay, the sequence of b sub k's are unbounded. Okay. All right, and then thirdly, the limit superior of S of n would be equal to negative infinity. This is basically the reverse idea, and that's going to be true if and only if the sequence S sub n goes to negative infinity as n goes to infinity. Okay, so the only way this can happen, the only way the limit superior can be negative infinity is if the entire sequence converges to negative infinity. Now notice that's not the case up above here, right? If just the supremums, if just the infimums converge to infinity, then the limit superior is infinite. But down here, the entire sequence has to converge to negative infinity in order for the limit superior to be negative infinity. Okay? Right? And then so a similar theorem could be developed for the limit inferior, right? This particular one pertains to the limit superior. The limit inferior could be developed along similar lines. Okay, I won't go through it, but I want to focus on two pieces of the proof for this first one. Okay, so I want to focus on part A of the limit supremum theorem. Okay, so let's just remember what we're looking at here. All right, so this is I want to focus on the proof of part 1, not A. Okay, so for part 1, we said, suppose the limit superior is a real value, right? Then that limit superior is equal to beta if and only if, for all epsilon greater than 0, there exists n naught such that S sub n is less than beta plus epsilon for all n greater than or equal to n naught, right? That's part 1. We'll prove that first. Part 2 says, in addition to that, we need to, for all epsilon greater than 0, given an n and a k, with k larger than n, greater than or equal to n, given an n, there exists a k with k greater than or equal to n such that S of k is greater than beta minus epsilon. That's the second part, which we'll prove. So let's start with the first part. Right, so the proof of part, sometimes my handwriting is terrible. Proof of part 1. Okay. And so we want to start with, we want to start with the assumption. So we assume that beta is equal to the limit supremum of S of n, right? And we know that that's equal to the limit as k goes to infinity of b sub k, where b sub k is equal to the supremum of the set S sub n such that n is greater than or equal to k. Okay, and so we're going to assume that beta is equal to this thing and it's a real number, right? And so what we need to show then is that the conditions 1 and 2 hold. Okay, and so let's let epsilon greater than 0 be given. Okay, so we've got this given, epsilon greater than 0. And what we can say then is that since the limit as k goes to infinity of b sub k is equal to beta, we know that there exists n naught in n such that b sub k is less than beta plus epsilon for all k greater than or equal to n naught. Right? And that's just the definition of the limit, right? That's just the definition of the limit. Then, since S of n is less than or equal to bk for all n greater than or equal to k, S of n must be less than beta plus epsilon for all n greater than or equal to n naught, right? Whenever you get out past n naught, this is going to hold. Okay. And that's the proof of part 1, right? So this proves part 1, right? We would say like part 1 of part 1. What about part 2? So this would be part 1 here. part 1I, we'll say, and now here's part 2. Okay. So for part 2, we need to, again, epsilon greater than 0 is given, and we let n natural number be given also. Okay, so we've got natural number, n. Now, we know that b sub k converges to beta, and we also know that b sub k, the sequence, is monotone decreasing. Right? Right, and so what does that mean? Well, that just means that b sub k must therefore be greater than or equal to beta for all k. Right? And so in particular, we can say, that b sub n is greater than or equal to beta. Right? And by definition of b sub n, given epsilon greater than 0, we know there exists a k greater than or equal to n such that, right, and here's the kicker, s sub k is greater than b sub n minus epsilon, which is obviously greater than beta minus epsilon. Okay. Right, and so that proves part 2. Okay. And so remember, this is an if and only if statement, right? And so we've assumed that beta was equal to the limit of s of n, right? And now we need to and we've shown that that produces 1 and 2. Now we assume 1 and 2 and prove the reverse. So this would be the forward direction that we just did, and now we need to do the reverse direction. So let's assume that 1 and 2 hold. Okay, assume 1 and 2 hold, and then let's let epsilon greater than 0 be given. Okay, let's let epsilon greater than 0 be given. Now by 1, we know that there exists an n naught natural number such that s of n is less than beta plus epsilon for all n greater than or equal to n naught, right? Right, that's just part 1. Okay. So hold on, let me rewrite that on the other side because we'll need to reference that. So let's see here. So by part 1, right, we know there exists an n naught such that s of n is less than beta plus epsilon for all n greater than or equal to n naught, right? So we've got that piece. Therefore, b sub n naught must be equal to what? Right? If this is true, b sub n naught must be equal to the supremum of the set s sub n such that n is greater than or equal to n naught, right? That's just the definition of that, right? And we know that that's less than or equal to beta plus epsilon. Okay, right? And then of course it follows, since b sub n is monotone decreasing, b sub n is less than or equal to beta plus epsilon. And this is going to be obviously true for all n greater than or equal to n naught, right? And so then the implication is that the limit superior of s of n is equal to the limit of b sub n, which is less than or equal to beta plus epsilon, right? And so because epsilon was arbitrary, right? Recall, well, since epsilon greater than 0 was arbitrarily chosen, right? What we can see is that the limit superior of S of n must be less than or equal to all beta. Right, beta plus even without the epsilon. Right, and so now we know that the limit superior is less than or equal to beta. So obviously what we're going to show is that it must be equal to it. Right, so to do that, let's assume there exists some beta prime which is equal to the limit superior, which is less than beta somehow. Okay. Okay. Now let's choose epsilon greater than 0 such that beta prime is less than beta, sorry, I need more space, such that beta prime is less than beta minus, we'll say 2 epsilon. Okay. All right. But then what? What happens? Well, we're obviously going to derive a contradiction. And what is that? Well, but then, right, there's going to exist an n naught such that S of n is less than beta prime plus epsilon, which itself would be less than epsilon plus epsilon. And this would be true for all n greater than or equal to n naught. Now, this would obviously contradict 2, right? Right, this would contradict part 2. Right, remember part 2 said that given some natural number n, you can find a k in n with k greater than or equal to n such that s sub k is greater than beta minus epsilon. But here we're saying there's going to exist an n naught such that s sub n is less than, right? Less than. Okay. And that would be the contradiction. That derives that contradiction. And so that being the case, it follows then that up here earlier we got that this piece is true, and so the second part of the proof of this piece of the proof is that indeed such a beta prime doesn't exist, right? So there's no value less than, right? Less than. So basically, the limit superior of S of n must be equal to beta. Okay, so that kind of wraps that one up. Very tricky proof. Obviously, what I would recommend is kind of go back through that, make sure all those pieces make sense, and make sure that you can follow it from section to section. It is a fairly tricky proof. We'll sort of wrap up this bit on limit inferior and limit superior with, I'm just going to kind of do a flurry here because I want to get to Cauchy sequences, but kind of a flurry of, I would say, kind of closely aligned theorems and corollaries, and I'll just kind of state all of these for reference. All right, so the first one is a corollary, I'd say, and it says that the limit superior of S of n is equal to the limit inferior of S of n if and only if, what do you think? Well, if and only if the limit as n goes to infinity of S of n exists in the real numbers, of course, or if the overall limit is infinite. Okay, so this should be hopefully common sense. If the limit superior and the limit inferior are the same value, then that must mean that the overall sequence converges, or it could happen that the overall sequence is infinite, positive or negative. Okay, so I should put plus or minus, right? Okay, so if the sequence converges, then the limit superior and the limit inferior are the same value. But if the sequence does not converge, then your lim inf and your lim sup are going to be different, or could be different. Yes. Oh, well, will be different if the sequence doesn't converge. Okay. Very good. All right, so that's that one. Then the next theorem, right, this just kind of draws out some of the additional properties and kind of stitches a few things up. So this is an interesting theorem here. Let's let A of n and B of n be two sequences that are bounded in R. Okay, so we've got two bounded sequences in R. Here's what we've got then. So this is a very tricky one. So what this one says is that the lim inf, the limit inferior of the A sequence, plus the limit inferior of the B sequence, right? So whatever this limit inferior is and this limit inferior, if I add them together, it's going to be less than or equal to the limit inferior of the two sequences added term to term. Okay. And that is going to be less than or equal to the limit inferior of the A sequence plus the limit superior of the B sequence. And that is going to be less than or equal to the limit superior of the A plus the B sequence added term to term, which would be less than or equal to the limit superior of the A sequence plus the limit superior of the B sequence. Okay, so there's a lot here, right? But basically, if I take the two, I mean, the way to think about it is that you start here, right? If I take the two sequences separately and I calculate the limit inferior, and I add those things together, that sum is going to be less than or equal to the sum of the sequence and the limit inferior of that sum. Okay, so this is not hard to believe. Okay. Then once I get here, I can say, well, certainly that is going to be less than or equal to this, right? The limit inferior of an plus bn is going to be less than or equal to the limit superior of an plus bn. But actually between there, you have this one, right? So the limit inferior of the one plus the limit superior of the other will be larger than the limit inferior of the sum, and it'll be smaller than the limit superior of the sum, right? So this one is kind of interposed between the two. And then, of course, over here, you've got the reverse relationship to here, right? So when I add the two terms together and take the limit superior, that's going to give me a smaller, less than or equal to value relative to the limit superior of the terms separately, of the sequences separately, right? So it's an interesting little theorem. It's a nice inequality that kind of shows the relationships of these things. And I think a lot of that is fairly straightforward, right? But this theorem really follows from the definitions of the limit superior and the limit inferior, right? And so you could prove this. I think it's relatively straightforward to prove. I mean, maybe a little bit involved, but you could really just kind of follow the definition of these inferior and superior and inferior limits. Okay. One more theorem, and then we'll call it for this section and get on to our Cauchy sequences. Okay, so let's let S of n be a sequence in R. So we'll let S of n be a sequence in R. And let's let E equal the set of subsequential limits. I'm going to write it out. The set of subsequential limits, the set of subsequential limits of S of n in I'll say R, or could be infinite limits as well. Okay. All right. So S of n is a sequence in R, and we're going to define this set E to be the set of all the subsequential limits of this sequence, right? So think of all the subsequences that are possible for a particular sequence S of n, and all of those subsequences have limits. This set E is going to be the collection of all those limits. Okay. Okay. Then what can we say? So this is going to be this is a beauty here. Then the limit superior of S of n and the limit inferior of S of n are in E. Okay, they're in E. And here's the nice part. Two things. The limit superior of S of n is equal to the supremum of E, and the limit inferior of S of n is equal to the infimum of E. Okay? So if I take the set of all the subsequential limits of my sequence S of n, then the limit superior is the biggest one, and the limit inferior is the smallest one. Okay, so that's not too hard to believe, but it stitches a few things up kind of nicely. All right. Okay, very good. We'll pause here, and I'll end part A, and we'll pick up part B with Cauchy sequences. So we'll see you in a few.